Good morning, friends. I welcome you all here in my course, Engineering Thermodynamics. Today, I am in last topic of the first module, that is the first law of thermodynamics and basic concept of thermodynamics. As of now, we have discussed about the basic concepts like systems, surrounding, boundary, equilibrium, quasi-equilibrium, zeroth law of thermodynamics, thermometry, first law of thermodynamics for control mass system we have done. Now, today, I am talking about first law of thermodynamics for open or control volume system for or flow system. So, as of now, we have seen that the mass which was there inside the system is remain there. It is not crossing the boundary. But here, during this open system or the control volume system, and this is also called the flow system, the mass will also move from one place to another place. So here some new concept is added. Mostly these concepts are very much suitable for the fluid mechanics or the flow problems like flow in tunnel, flow in pipe, aerodynamics, and some other issues. These things can be handled very nicely. So I thought that we should discuss about first law of thermodynamics related to the control volume system. So if you want to solve the problem from mass to control mass to control volume, we need some modification. Most of the basic laws like Newton's laws and other things, they are derived with the help of the control mass system. So we have to convert from control mass system to the control volume system for the flow condition of the fluid. Here also mass, momentum and energy equations are used, and these equations for control volume system is slightly differ from the control mass system. The first person who has made this mathematical formulation was the Reynolds. So the theorem which deals with transferring control mass to the control volume system, the Reynolds transport theorem is used. So I am going to discuss this, and after that I will go for the deriving of the energy equations on control volume system, then mass equations and momentum equation. These all things will be seen here, and you see that how these things are useful and how this can be applied for any flow systems. Today's content, I am going to discuss about first law of thermodynamics, Reynolds transport theorem, conservation of energy for control volume system, steady state energy equations. So these things I am going to discuss today. So you know that the first law of thermodynamics, we have seen that del Q is equal to dE plus del W. So if you supply a heat, this is the Q heat. If you supply the heat, some work will be done, delta W, and some energy will be stored here. It is a delta E. So this delta Q is equal to summation of stored energy plus work done by the system. As you know, this work and the energy, they are the partial derivatives, and this work and the heat is a partial energy, but this energy is a accurate or the proper differentiation. So this is the property, and these are not the property. Okay, so this we have discussed in detail in earlier also, so it is not a much issue. So now we have to see that how we can go and how we can convert, and this we have derived in control mass system. Control mass system, in this mass will be inside this boundary. So whatever amount you have inside this mass is constant. It is not crossing this boundary. Only energy, maybe heat or the work, this may transfer, but not this mass. Mass will remain constant. But here mass will also shift from, if it is a control volume system, suppose here is moving from here and some mass is moving from here out. This is the out and this is the in. So there is some displacement of the mass which is also present in the system that we are going to handle today. So here we can see that first law of thermodynamics is conservation of energy, and we will be also seeing the application to an open system, and this open system is also known as a control volume system. So here we can see that we have to use a theorem which is called the Reynolds transport theorem, which makes the control mass to be converted as a control volume, because most of our derivations are on the control mass system. So same way this all things are working. So we will be discussing about Reynolds transport theorem. We have seen that control mass system is a deformable system, but need to convert from control mass to control volume system for the flow condition. Physical laws are postulated for control mass system. Most of the laws which are made or derived, they are on the control mass system. If we have an extensive property, then rate of change of property n. So what is the Reynolds transport theorem? Just I am describing here. So if we have an extensive property n, then rate of change of this property n in a control mass system is equal to the rate of change of n in a control volume system plus net rate of efflux from the control volume system. So how much it is going out? So the control mass system, the rate of change of the property n in control mass system is equal to the rate of change of n in a control volume system plus net rate of efflux from the control volume system. So this is the your definition, or the Reynolds transport theorem is this is the Reynolds transport theorem. So here we will be discussing in detail about this thing. So actually what is the meaning of this thing we can discuss here, that if this is the your control mass system here, and if it is in and from here it is out, the velocity is in this direction. So in this side, this is the out. So in outside, if you see, this is the velocity vector, and here also the velocity vector. But if you see this perpendicular to this area and perpendicular to this area, if you see, here is this is the n. It is a in this direction, and here if you see, this is the n in this direction. So if you want to convert from control mass system to control volume system, and if there is a property, so we can say that the this rate of change of the property n, assume it is a n here. So this dn, so here dn by dt is equal to del of del t neta rho dv. Here this is the volume here, plus this is in control volume and this is the control surface. This is the neta rho v dot n into dA. So this is what? This is the net rate of efflux. Net rate of efflux in CS means control surface. And here this is the control volume. So this is the statement for the Reynolds transport theorem. So this we can see here that all laws are derived as control mass systems. If n is the extensive property in a control mass system, that is CMS, so the rate of change of the property n is equal to rate of change of n, rate of change of n in a control volume system plus rate of change of efflux of n in a control volume system. So here this eta is equal to a specific property. Eta is what? It is a specific property per unit mass. So if the property is here n, so n by m is a property per unit mass, and this is also called the specific property. So this dn by dt in control mass system is equal to del of del t neta eta rho dv plus eta rho v dot v vector dot n vector into dA. So this is in control surface. If this n is the property which is energy, n is we assume as energy, so this eta is equal to energy per unit mass. So this we can see here that, so this will be, now we can write here that del of del t, here in place of this eta we will put here E as a specific energy. So here E, small e is equal to capital E divided by m, and this is the E, and this is a specific energy. So here we can put here that dE by dt is equal to del of del t at control volume integrated, here E rho del dV, V is here volume, plus, so this integrated in CV, so E rho V dot N dA. So here it is a mass flow rate. So this we can see here that how these things are happening. So here we can see here this is the here total energy when integrated with control volume system, and this is a mass flux rate. Here this is a rho V and dA. So what is here N? This you can see here. It is the area is A here, and perpendicular to this area, this direction is your N. And same way here, if it is V is in this direction and N will be up perpendicular. So here it is inside, it is a minus, and this is the out is a plus. So N is plus and here N is minus. So here we can write that del ECV, this is the total energy, del ECV by dt plus here E naught means out. EO means E out, and this is the mass. So dm naught by dt minus dei. So here energy is ei, here energy is eo, and here mass is mo, here mass is mi. So here it is a efflux, rate of change of mass in and out. So this is out minus e, because here e, we have put minus because this n direction is opposite to the motion of the, or the vector, v vector of this system. So here n is equal to energy. So this small n is equal to E by m, and it can be a mass, momentum, or the energy. Here this n can be any property. It may be mass, momentum, or energy. We will be seeing here the conservation of mass, conservation of energy. Both we can see in this derivation. So we can see here that minus ei comes as a outward, because this n vector is positive for the outward. Inflow, n is negative for inflow, it is negative. So writing this inflow and the outflow mass flux, we can see here that here integration of inflow ei rho vi into I vector, these all are the vector, minus I vector. Here minus, it is I is minus in this direction, plus dai plus integration E naught rho v naught I, these all are vector, dot, this is also positive dA naught. So here this is the dA naught, here is the dAi, this is the in and this is the out. Okay, so here velocity is v naught, here I vector is positive, here I vector is negative. So here if you write here, this is the control volume system, here vi, I in this direction is positive, but here we are getting this n in this direction, so it will be negative. Okay, so here we have, here if you see, we have put the minus I, because direction of I is in this direction, perpendicular to this surface. So here we will get minus ei integration rho vi dai plus E naught rho v naught dA naught. So minus ei, this is the rate of change of mass which is entering. So dmi by dt plus E naught dm naught by dt. So we can write the final equation like this, that dE by dt in control mass system is equal to dE by dt del E by d del t plus E naught dmo dm out by dt minus ei dmi by dt. So what is dE by dt for a control mass system? So we have to see that what is the dE by dt for the control mass system. We have to use the first law of thermodynamics for control mass system, which we have already completed in our previous classes, and we know that the change in heat delta Q is equal to dE minus delta W, means heat gain and work done. So this, from here we have to put this value of dE, and we can get this thing as, so here we can see that if we integrate with respect to the t, so del Q by del T is equal to dE by dt plus del W by del T. Q and W are the path function, so del Q plus del E. So we can write that dE by dt is equal to dQ by dt minus dW by dt. So here we can see that we have to write plus. So dE by dt is equal to del Q by dt minus dW by del W by dt for constant mass system. So we now substitute in our energy equation dE by dt is equal to del Q by del T minus del W by del T. So in this, if you see this equation, we have to, in place of dE by dt, we have to put which we have got dQ by del Q by del T minus del W by del T is equal to del ECV by del T plus E naught dm naught by dt minus EI dm I by dt. This we have substituted this value here in place of E. This is in place of E. So now this we will shift from right side to the left side. So del ECV by del T is equal to, this will be the positive. So EI dmi by dt plus del Q by del T minus E naught dm naught by dt minus dw by del T. So if assume there is no flow, so dmi by dt and dm naught by dt will be 0. So this will be 0 and this will be 0. So we will get the same dCV is equal to del Q by del T minus del W by del T. So what are those specific energy? Okay, now we have to make it in the specific energy. And if you know that if the velocity is very less, and we can assume that this E is equal to U plus PV plus V square by 2 plus GZ. This is the potential energy, this is the kinetic energy, this is the pressure energy, and this is the internal energy. So here the total energy, specific energy E is equal to specific internal energy plus work done plus kinetic energy plus potential energy. So this is the total energy, total specific energy on the system. So we can write here that del ECV in control volume by dt is equal to UI plus PI VI. This is the volume here and here is the velocity plus VI square by 2 plus GZ1 dmi by dt plus del Q by del T minus U naught plus P naught V naught. This is your volume plus Q 0. Here we have left the V naught square by 2 plus dm naught by dt minus dw by dt. So this is the general energy equation for the control volume system. So we can see that this is the internal energy, total energy plus heat energy minus total energy out minus dw by dt. So this is the equation, general equation for energy, and this we can see that for any type of flow system, now this control mass is converted to the control volume system. This you can see dE is CV by dt. Any property we can change in such a way. But if you know that for the dmi minus dt, dmi by dt minus dmo by dt is equal to dmcv, control mass by dt. So if you see that this is equal to 0, if it is 0, then d means input, rate of change of mass in is equal to rate of change of mass out is equal to no mass. So it becomes CMS will become CVS. Control mass system will be as a control volume system. That is why we wanted to say that how these things can be transferred from one form of equation to the another form of equation. These equations are useful for the flow dynamics, like fluid dynamics, to find out the flow behavior of the system. So we need to use this equation for the finding out the different properties. So the control mass and the control volume systems are same, and this is called the steady state case. So this is called what? Steady state case. So if rate of change of mass in dmi by dt is equal to rate of change of mass in outside, both are same, then we can say that this system is in steady state condition. So now steady state energy equation. We have just now we have find out the general equation for the energy state, and if del E CV by del T is equal to 0. If so, this right side UI plus PI VI plus V1 square by 2 plus GZI DMI by DI dt plus del Q by del T is equal to, this is the input, inflow is equal to outflow. So U out plus P out V out plus V out square by 2 plus G Z out here dm out by dt minus dw by dt. Writing per unit mass, so we can write that dm by dt. So ui plus pi vi plus v1 square by 2 plus gz1 plus del q by del m is equal to u naught plus p naught v naught plus v naught square by 2 plus g z naught plus dw by del m. So we can see here that this potential energy gzi and gzo both are 0. Mostly they are in the same line. Any mechanical system, they are not will be very high. One end will be high and another is very low. So for steady flow energy equation, mass of kinetic many times kinetic energy and potential energy are negligible. So this is also 0 and this is also 0. So we will get here dq minus dw here, dq by dm minus dw by dm is equal to, this is h naught minus hi, where h naught is equal to enthalpy at outflow and hi is equal to enthalpy at inflow. So these things for the compressor and the turbine only work and no heat. So if you want to study about the turbine and the compressor, this dq will be 0, and if you want to study about the nozzles and the diffusers and all, that time dw will be 0 and dq will be there. So this h naught minus hi, and this is the for steady state equation for steady state energy equation in form of enthalpy. So we got the application of this control volume system. This can be used for nozzles, diffusers, compressors, turbine. So many mechanical advantages are there, where the flow is moving from one place to another. In this, by first law in the control volume system can be used. In this, we take the assumption that potential energy and the kinetic energy, change in the potential and the kinetic energies are negligible. But the kinetic energy cannot be neglected for the nozzles and orifices or from diffusers and all. We cannot change, we cannot take that kinetic energy cannot be taken as negligible for case of nozzle because their velocity difference is enormous. So we cannot take negligible. Okay, so in this next topic, I will be discussing about second law of thermodynamics, and we will see that how this from we are moving from zero law to the first law. Now we will go for the second law of thermodynamics, and we will do some numericals also in that topics, and hope this will be very useful for the all the people. These are the references which I have taken: Eunice Sengel, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hills. And this is the NPTEL lecture. You all can see this and join and get your things done. Any questions, you are welcome to ask to my email. You can send ydwedi@gmail.com. Please do like and subscribe this channel, and it will give me the moral boosting. And if any query, you are welcome to comment and give the feedback. Thank you very much for the joining. We will see you in the next class with a very energetic manner. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.